afternoon. I'm Saritha Kumari, Assistant Professor, Electrical Department, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Under the course, Performance of Transmission Lines and Cables, today the topic is Advantages and Disadvantages of Corona. So this topic is mapped to course outcome 4. So in my previous lecture, I have explained about the corona phenomena, what is meant by corona basically, and how it causes in the power transmission lines. And also we have given a basic definition under corona, that critical disruptive voltage, VC, denoted with VC, which is given as this critical disruptive voltage. It is given as its expression G naught R log base E D by R. So this is a basic expression, and when the air density factor, this is a basic expression, the voltage, critical disruptive voltage at which corona starts under normal weather conditions, that means at standard temperature and pressure, and when different weather, because we have various weather conditions, then the temperature and atmospheric temperature and pressure changes. Then there is based on those conditions, there is one more factor that is included here, delta, that is called air density factor. So that it has its own expression, 3.92 B by 273 plus T. That is explained in the last lecture. And also one more factor based on the conductor surface condition. So conductor surface condition is included in this expression with a factor M naught. M naught also there in this expression. So basically this is the expression for critical disruptive voltage, delta G naught M naught R log base E D by R kilovolts per centimeter. So kilovolts per centimeter. So where delta is the air density factor in terms of its expression in terms of pressure, atmospheric pressure and temperature, and delta naught is the gradient, potential gradient, whose value is for the conductor voltage gradient. Its standard value is 30 kV, its maximum. If it is RMS value, 21.2 kilovolts. Then what about this M naught? It is a surface conductor surface factor. So its value based on for polished conductor, it has some value, and for rough conductor, irregular surface, it has another value. Less than 1 only, 0.7 to 0.8 like that. Usually, that is the range of M naught. Then and if the problem is given in the problem, if they ask you to calculate critical disruptive voltage, all these parameters they will mention. If it is not mentioned, we have to assume that delta is 1, M naught is 1. Standard values. If they clearly given particular weather condition and temperature, we have to calculate this delta. And also M naught also they will give. This is a value for the conductor based on the conductor surface. So that is how they will give the problem. Then G naught is standard value. Conductor potential gradient, G naught, its RMS value 21.2 kilovolts, and R is the radius of the conductor. Generally it's they will give in the problem, and distance between the conductors. That will also they will give in the problem. So that is how basically critical disruptive voltage is defined, and its expression that is covered in the previous lecture. Next next definition is visual critical voltage. what is this? In the name itself, it is there, visual. Okay, that means it is a voltage, minimum phase to neutral voltage at which corona glow appears. That means with our eye we can see the corona clearly in the, okay, because of this glow. We know that when corona occurs, there are certain things takes place, like there will be a violet glow. Okay, that is basically corona. Okay, occurs, that these are the things will happen. So that is already we have seen in the previous lecture. There is a violet glow and hissing noise, right? That means based on the they have the definition, this critical visual critical voltage. It is a minimum phase to neutral voltage at which corona glow appears all along the line conductors. Okay, so that is how the definition is given. Now the expression for this, there is a expression for this visual critical voltage also. Okay, it is given by, of course it is per phase voltage only. Okay, previously this one also per phase value only. Okay, for per phase expression. So the visual critical voltage denoted with V suffix V, it is given by, okay, same factors. Okay, like we see, only the additional factor is, okay, this is the additional factor. So expression is mv delta, okay, mv g naught delta r, okay, mv g naught delta r. Okay, we know that what is m, it is a irregularity factor based on the conductor surface. G naught, okay, potential gradient. So then delta, okay, r into, in brackets, 1 plus 0.3 by root of delta r, log AC d by r kilovolts per phase. So this is the expression for visual critical voltage. Now, so here this MV value is 1 for polished conductors. Okay, it is okay. Previously it is M naught, right? Now for visual critical voltage, it is denoted with M suffix V. Okay, and its value is 1 for polished conductors, 0.722 to 0.82 for rough conductors. Okay, so that is about the visual critical voltage. Next, power loss. We know that when corona takes place, there is a hissing noise, there is a violet glow. Okay, so all these things takes place. So they say that some power is wasted in the form of hissing noise, means in the form of sound energy. Violet glow, okay, in the form of heat energy. So like that, they say that some energy is wasted, some power is wasted. So they have the expression for this power loss due to the corona. So formation of corona is always accompanied by energy loss, which is dissipated in the form of light. Okay, light, heat, sound, chemical action. Okay, as I mentioned, because there is a violet glow, so in the form of light. Okay, there is a ionization of air surrounding the power conductor, means conductor gets heated up, right? So like that, there is some power is wasted in the form of heat. Sound means hissing noise, power wastage in the form of sound energy. Next, production of ozone gas. So power, we know that corona is accompanied by production of ozone gas, that means chemical action. So all these factors, okay, it's said as power loss. Okay, so now the power loss expression, okay, is given by, so this happens when the disruptive voltage is exceeded. Okay, when the applied voltage. When the applied voltage is greater than the critical disruptive voltage, okay, then corona comes into picture. Automatically power loss takes place, and the expression for this power loss is, okay, denoted with letter P, 242.2 into F plus 25 by delta. What is the system supply frequency in hertz? Okay, F plus 25 by delta under root of R by D into V minus Vc whole square into 10 power minus 5 kilowatts per kilometer per phase. So this is the expression we need to remember. Okay, because problems are there to calculate this power loss also. Okay, 242.2 into F plus 25 by delta under root of R by D into V minus Vc whole square into 10 power minus 5 units are kilowatts. Okay, the power loss expression for corona, due to corona, it's given in terms of kilowatts per kilometer. Okay, per phase. And here we know what is Vc. Vc is a critical disruptive voltage, and other remaining factors are well known. Right? F is a supply frequency in hertz. V is a system phase voltage. Right? System operating phase to neutral voltage. Okay, it's RMS value. And Vc is critical disruptive voltage in RMS value. Okay, it's also RMS value for phase value. Next, advantages and disadvantages of the corona. So it's they said that there are advantages and disadvantages because of this corona. In the correct design of overhead transmission line, high voltage line, a balance should be there between the advantages and disadvantages. Okay, so in the designing, okay, during designing for the designing of high voltage line, okay, conductors, high voltage transmission line conductors, they design the conductor in such a way that, okay, there is a balance between the advantages and disadvantages because of corona. Okay, we know that because basically what are the factors affecting corona? In the starting last lecture we have seen, okay, conductor diameter, conductor surface condition, distance between the conductors. Okay, so these are the various factors, right? So they keep in mind. Okay, now first advantages. Due to the corona formation, the air surrounding the conductor becomes conducting, right? That is what happens. The air surrounding the conductor becomes ionized. Okay, that means conducting, and hence virtual diameter of the conductor is increased. Okay, so then what happens? The virtual diameter of the conductor increases, and the increased diameter reduces the electrostatic stresses between the conductors. So they say that this is what, because of this increased diameter, virtual diameter reduces the electrostatic stresses between the conductors. Okay, between the side by side conductors. Now, second point, corona reduces the effects of transients produced by surges. So this corona reduces the effects of the transients, which are generally caused by surge. We know that during stormy weather conditions, when lightning, thundering, lightning takes place, we have this, right? So the huge voltage, that is nothing but transient voltage, right? So they say that this corona reduces the effect of those surges, transient voltages. Next, disadvantages. At the same time, there are disadvantages. So as we all know, first thing, corona is accompanied by loss of energy, power loss, right? Just now we have seen the equation for that. So it is accompanied by power loss, that is loss of energy. This affects the efficiency, transmission line efficiency. Okay. Next, second point. Ozone is produced by corona and may cause corrosion of the conductor. Okay. it produces ozone, right? The corona. So what it may cause corrosion of the conductor. It may due to the chemical action. Third point, current drawn by the line due to corona, okay, is non-sinusoidal. Because of this corona, the current in the line is non-sinusoidal. Hence, non-sinusoidal voltage drop occurs in the line. This may cause inductive interference with neighboring communication lines. So, there are chances for the interference with neighboring communication lines. Okay, these are the disadvantages of corona. Okay, so one is power loss. It may affect the transmission line efficiency. Second point, it may cause corrosion of the conductor because of the ozone gas production. Third point, it produces non-sinusoidal current in the line. It causes, which may cause non-sinusoidal voltage drops in the line, which may result in interference with neighboring communication lines, which is not good for the healthy for the line operation. Okay, these are the disadvantages. Okay, so these are the disadvantages. Okay, so of this karma. Okay, so with that we have completed the theory part of corona. Almost we completed. Next we have a small problem here. A three-phase line has conductors 2 centimeters in diameter spaced equilaterally 1 meter apart. Okay, diameter of the conductor 2 centimeter and the distance between them is 1 meter. And the dielectric strength of the air is 30 kV maximum. Okay, that means delta is given. Okay, the delta naught is given. It is 30 kV. It is maximum value per centimeter. Of course, it is standard value. We already knew that. If it is RMS value, 21.2. Okay. Find the disruptive critical voltage for the line. They ask VC. Okay. Take air density factor delta is equal to 0.95 to regularity factor M naught 0.9. Delta and M naught values directly given. So simply the thing is here, recollect the expression for disruptive critical voltage, standard expression. So M naught, okay, M naught delta, sorry, this is not delta. What is that? Dielectric strength of the air, G naught, right? So G naught into delta into R into log base E D by R, kilovolts per centimeter. So this is a standard expression to calculate VC. Here directly given M naught 0.9, delta 0.952. What is the G naught? Dielectric strength of air. It's 30 kV. Of course, it is given maximum, but we substitute here RMS value, right? 21.2 kilovolts. Okay, next, radius of the conductor. What is the radius of the conductor? Diameter is 2 centimeter, so radius is 1 centimeter. Remember, we substitute in centimeter because the equation is, okay, the equation for VC is per centimeter. So we substitute D and R in centimeters only. D and R in centimeters only. Now, space equilaterally 1 meter means distance between the conductors is 1 meter means 100 centimeter. Okay, so substitute all these values. So 0.9, 21.2, 0.952, 1 log base E 100 by 1. This gives, okay, answer. Already we have the answer, okay, written here. So if you calculate using scientific calculator, we'll get 83.64. What are these units here? Kilovolts per centimeter, and this is for phase. Okay, the equation is already we know that. Okay, this equation for VC give for phase value. Okay, if you want line VC, line to line, what we will do? Root 3 into 83.64. Okay, so that gives the line value. Okay, this is the phase value using the equation, standard equation that gives the standard value for phase value. And if you want line value of the disruptive critical voltage, multiply with root 3. Okay, so this is how, for using given data, how we can calculate disruptive critical voltage of the line. Okay, so these are the references for this lecture. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.